Welcome and thank you for watching. We'll give a quick overview of how our team developed the interactive engineering fountain, covering our design process, prototyping, testing, and final outcomes. We are Team 14 of Engineering 131, Section 215. My name is Ty Tran and I serve as lead engineer. Oliver Walseth coordinates our testing and edits our videos. Luke Kavanaugh manages model fabrication and documentation, and Tree Nguyen leads our prototyping work and AI-driven concept research. Purdue Engineering is celebrating its 150th anniversary, and the college is looking for interactive scale models of campus landmarks that connects visitors with past, present, and future of engineering at Purdue. Our team's goal was to design a low-cost, reusable, and interactive display that incorporates microelectronics to educate and engage users. The purpose of this project is not just to create a model, but to highlight Purdue's long history of engineering innovation and to inspire future engineers through a hands-on, meaningful experience, which directly aligns with the sesquicentennial theme of training engineers. For idea generation, our team began by exploring a wide range of concepts. From all of these early ideas, we selected 3 strong candidates to develop further. We then turned each one into a testable prototype so we could compare their usability, interaction, accessibility, and overall appeal. This process helps us objectively determine which design best met project's criteria and constraints. After creating our 3 prototypes, the bell tower, the interactive engineering fountain, and the turtleneck, we moved into the testing phase. We had 5 testers evaluate each design based on key criteria, such as ease of interaction, visual appeal, accessibility, safety, and numbers of inputs and outputs. This allowed us to gather consistent, comparable data across all concepts. After collecting our test results, we organized all the scores in a metric scoring table. This helped standardize what each score meant from 1 to 5. We then placed the scores in a weighted decision matrix where each criterion was assigned a weight based on importance. Applying these weights allowed us to compare the designs more realistically. The interactive engineering fountain scored the highest overall, making it the strongest choice for our final design. After some feedback, we made a couple changes and ended up with this final design of the interactive engineering fountain. It works by using a small pump that pushes water up through the center column. The water then flows down a slope base back into the reservoir, where it's then recirculated. A water level sensor constantly monitors the amount of water in the system, and the microcontroller automatically turns the pump off if the water level gets too low and back on if it's above the minimum threshold to conserve energy use. Users interact with the design through buttons that control LED colors and patterns and the start of the automated sequence, along with a red emergency stop button for safety. The model also includes splash guards to help manage water movement and a non-slip rubber mat at the base. This mat keeps the fountain stable on smooth surfaces and reduces slipping hazards from any small splashes. We made a scaled-down version of this final design, and the CAD model guided that process. It helped us plan the structure and see how each component would fit together and test the visual features. To help visualize the automated sequence, my hand represents the water level in the system. When the water level goes below the minimum requirement, the fountain automatically turns off. Once the level goes back above the minimum, the fountain turns itself back on. You can see the LED controls demonstrated on the microcontroller. One button changes the LED color, while the other button changes the blinking pattern. This shows how the users will interact with the final design through simple, intuitive inputs. To estimate the total cost of our final design, we gathered prices for each major component shown here. One of the largest expenses in the project comes from the acrylonitrile styrene acrylate, or ASA, 3D printed structures that form the main body of the fountain. To get accurate pricing for these parts, we used Xometry's online manufacturing estimator, which provided detailed cost estimates for each structural piece based on size and material. By combining the Xometry estimates and the cost of the electronics and accessories, our total projected cost came to $4,952. This model's lifespan is strengthened by several durability features. ASA construction resists UV light and moisture, helping the structure last over time. Its modular design allows individual parts to be replaced when needed, extending the system's overall life. The electronics are protected in enclosed housings to prevent damage. The design is built to be reused for at least 8 full installations and with proper maintenance. Our final design meets all project requirements. It stays within the $5,000 budget, follows the 1 to 20 scale, and is durable enough for at least 8 uses. It offers strong interactivity between multiple inputs and outputs, fits the training engineer's theme, and sets up in under 3 hours and uses very little energy. With great aesthetics and solid accessibility features, the design successfully meets all performance goals. Our design does have some limitations though. Water can splash and make the setup messy. It can only be set up near water sources, which limits the areas of use, and disposing of the water is difficult indoors. It also needs more accessibility features. In the future, better splash control, portable water system, and improved accessibility could make the design easier and safer to use. Thank you for watching our video, and we appreciate your time and hope you enjoyed learning about our design.